Hello. Now today we will work on another drawing the internal force diagrams of another frame. So let me draw the structure here. Now I have an internal hinge here, an inclined member, another internal hinge, inclined member and another internal hinge. I have a point load that's 20 kilonewtons in magnitude, but it's applied to the middle, so let me redraw it one more time. This is 20 kilonewtons, so this distance is 0.6 meter, 0.6 meter. That distance is 0.8 meters. I have a point load also here in the horizontal direction. That's 30 kilonewtons. And let me draw this is 0.8. This 30 kilonewtons is applied at the middle, 0.6 meters and 0.6 meters. Okay, and let's put the labels. This is point A, point B, C, D, and E. So when we investigate that structure, now here I got three support reactions here, which gives me 6 unknowns. I got 3 equilibrium equations. In addition to that, I know that moment at these 3 locations are equal to 0. So this gives me 3 additional equations. So total 6 equilibrium equations, and I can say that this structure is in equilibrium. So let's do the discretization. Again, let's divide this structure into members and nodes and show the degrees of freedoms. Okay. So wherever we have a discontinuity, I have to assign a node. So these are all nodes for me. And let's draw it, the discrete version of the structure. This is point C, member CD, point D, member DE, node E, and I have node AB, member AB, and node A here. So these are all nodes for me. So at the end of the day, what I have in the structure is 1, 2, 3, 4, 5 nodes. 1, 2, 3, 4 members. Okay, now let's assign the degrees of freedoms. Now here it's a fixed support. I don't have any degrees of freedom. Now let's go to point B. It can move in the horizontal direction. That's the first degrees of freedom. It can move in the vertical direction. That's second degrees of freedom, and it can rotate. That's the third degrees of freedom. Now let's go to node C. Translation, yes, D4. Vertical translation, yes, D5. And remember that I have an internal hinge here, which means that I got 2 different rotations. I can have 2 different rotations at both ends of that internal hinge. So I'm showing it like that. I got D6 at this end, D7 at that end, which shows me that I can have 2 different rotations at these members. Let's go to node D. Translation, D8. Horizontal translation, vertical translation, D9. And again, I got an internal hinge here. Again, I have 2 different rotations. So let's show it. This is D10 and D11. And finally, I'm looking at this node. It's a fixed support, but at the same time I have an internal hinge, which shows that this member can rotate. This member can rotate freely in either direction, so I should put another degrees of freedom here, D12. So this structure has 12 degrees of freedom. In other words, the degree of kinematic indeterminacy in this structure is 12. Here, of course, we didn't assume no axial rigidity, so let's put it as a note, no axial rigidity in this structure. Change that. Okay, now the next step. We discretize the structure. Now let's draw the free body diagram. This time I will not start from the support reactions. I will calculate it while drawing the free body diagrams. So I will just draw it a little bit larger this time. I'm just showing all the nodes and members. Let's show the loads. So I have 20 kilonewtons here and 30 kilonewtons here. Now the question is, where do I start? Now, if I take moment with respect to that point, that should give me nothing, because I don't know what this moment is. I don't know what this vertical force is. So I have two unknowns, right? Again, the forces in Y, I got two forces. So by just writing the three equilibrium equations, I cannot directly obtain the support reactions. But if you take a look at this member, right? This member, at both ends, the moment is equal to 0. So if I take moment with respect to that point, that should give me the horizontal reaction. So let's do that. Let's start from the member. That's different from our previous approach. So if I take moment with respect to point D, I find out that this force should be equal to 15 kilonewtons. Okay, so 15 kilonewtons is the horizontal force. Now again, at the same structure, at the same member, I'm writing the sum of horizontal forces should be equal to 0. So from that, this gives me that this force should be equal to 15 kilonewtons also. So that's all the information that I can get at this point. So let's transfer this force here, 15 kilonewton. I should have the same force but in the opposite direction. Now this node is in equilibrium in the horizontal direction, and I should have same force in the horizontal direction. Okay, now let's take a look at this point now. Now we have an internal hinge here, so I know that moment at point C must be equal to 0. So at this end of the member, moment should be equal to 0. And again, since I have an internal hinge here, I know that the moment at this point is equal to 0 also. So if I take moment with respect to that point, that will give me the vertical force at this end of the member. And if you do the calculation, that force will be equal to 15 kilonewtons. All right, again, let's repeat. I'm taking moment with respect to that point. So this 15 kilonewton will create a moment in this direction. The magnitude of that moment is 15 times 0.8. In order to balance it, I need a moment in the opposite direction. The the moment arm is 0.8, so it tells me that this force should also be equal to 15 kilonewton. And now the moment at this end, I know that it's equal to 0. And if I write the vertical force equilibrium, I find out that this force should be equal to 15 kilonewton, and that force should be equal to 15 kilonewton. Now, right now, this member is in equilibrium in both horizontal and vertical directions. I can transfer this vertical force to the node D. So I should have 15 kilonewton here, 15 here. Transfer it to the member. I see that I should have a compressive force here. Now transfer these forces to the support. Same force in the opposite direction, same force in the opposite direction. And I find out the support reactions at node E. The horizontal support reaction is 15 kilonewton and the vertical support reaction is 15 kilonewton. So these are the support reactions at point E. And then I can calculate the support reactions at point A, okay, because right now I know these two support reactions. So if I use the horizontal force equilibrium, so the sum of this one and that one should be equal to 30. So this gives me that the support reaction at this horizontal support reaction should be equal to 15 kilonewtons. And the vertical reaction is 15 here. So this one plus the vertical reaction here should give me 20 kilonewtons. So this tells me that I have this 5 kilonewton as my vertical force. Now, the other thing that we can write the moment equilibrium if I take moment with respect to point A and calculate the moment due to that 15, 30, and 20 with respect to point A. And I can at the end find that in order to balance these moments, I should have a moment that's equal to 26 kilonewton meters. So once we determine the support reactions here, I can determine the other support reactions at point A. Now let's continue. I will continue from node C. So I'm transferring these forces to node C. Vertical force in the minus x direction, and like that. And here I have 15 kilonewton as my vertical reaction and 15 kilonewton as the horizontal reaction. Now I'm writing the equilibrium equation for this member. In the axial direction, this should be equal to 15 kilonewtons. The vertical reaction should be equal to 5 kilonewton. And I know that moment is equal to 0. I'm taking moment with respect to that point. I have moment due to 20 times 0.6 minus 15 times 1.2. So in order to balance that moment, I should have another moment here whose magnitude is 6 kilonewton meters. I have to apologize because I forgot to show that I have an external moment here. I have to write it here. This is 10 kilonewton meters. I forget to write it. So I have 10 kilonewton meter, an external moment at this node. Okay, that was the original question. So now this member is now in equilibrium. Let me show these 15 kilonewtons here also. All right, now we are at this node. Okay, so I'm just transferring these forces to that node. So let's do that. Vertical 5 kilonewtons, 15 kilonewtons, and the moment that's equal to 6 kilonewton meters. and I have 10 kilonewtons here in the opposite direction, 6 here. In order to balance that moment, I should have another moment in this direction. Magnitude is 4 kilonewton meters, vertical force, horizontal force. So now, after that, this node is in equilibrium. So transfer all the nodes to the ends of the member. So I have a moment that's equal to 4 kilonewton meter. Vertical force magnitude is 5 kilonewtons. And the horizontal force magnitude is 15 kilonewtons. Now I'm writing the equilibrium equations for this member. I should have 15 kilonewtons in that direction, 5 kilonewtons in this direction, and I'm taking moment with respect to that point. I got 4 kilonewtons in this direction, and I have 15 times this distance is 2. 15 times 2 gives me 30 minus 4, and I should have a moment that's equal to 26 kilonewton meters. Transfer that to the node in the vertical direction. This is in the horizontal direction, and check if this node is in equilibrium. Yes, it's in equilibrium, so we can just, that's a verification. So we can say that now all these members and nodes are in equilibrium. Okay, so the next step is to draw the internal force diagrams. So let's use this figure. Let me show the sign convention here. That's our starting point. Sign convention. This one will show the positive directions. Tension, that's the shear, are positive directions in shear and positive directions in moment. Let's start from the axial force diagram. Now here I have an inclined member, right? But this is we don't really, these forces are not along the element axis or orthogonal to element axis. So they don't really mean much to us. We have to convert them. We have to find their components. Let me draw it in here with a different color. So this is our member. I have to find the components as axial forces and shear forces. Okay. So I have to convert these 15 and 15 kilonewton force couple into another force couple that means something to me, an axial force and shear force. So we do a coordinate transformation. We use just geometry here, right? I know that this angle is 45 degrees. So I need to calculate the components. Let me show 15 and 15 here. The components of these two 15 kilonewtons in terms of N and V, right? So V, if I write V, is equal to, I have the component in the V direction as follows here, and another component of this one in this direction. Okay, so V is equal to, and all these angles are 15 times cosine 45 minus 15 times sine 45, that's equal to 0. So the shear force is equal to 0. The axial force, I have to find this component plus that component of both forces. So 15 times sine 45 plus 15 times cosine 45 will give me, I'll just write it in here, 21.21 kilonewtons, and the axial force will be in this direction, and magnitude is 21.21 kilonewtons. Now here what I did is, again, let's repeat, these are not along the element or perpendicular to the element axis. So these are some end forces, but they are not axial or shear forces. What I need to draw these diagram is the axial or shear forces. So I'm just calculating the component of these two force couple in V and N directions. And there I'm using just the geometry. This angle is 45, and from trigonometry I obtained that the V is equal to 0, no shear force, and N is equal to 21.21. It makes sense actually. Why? Because take a look at this member. I have a hinge here, another hinge here, no loading on this member, so this is nothing but a truss member. It only carries axial force, nothing more. And with this free body diagram and this transformation, we just show that. Okay, now after doing that, now we are ready to draw the internal force diagrams. Let's start from the axial force. Let's draw our structure first. So I'm going from bottom to top, left to right, and bottom to top, and this is my axial force diagram. So I'm going member by member. This is the first member. It's under compression. Magnitude is 5 kilonewtons. It's negative 5 kilonewton. Now the second member is this one. It's again under compression. The magnitude of the compressive force is 15 kilonewtons, and it's negative also under compression. This is minus, magnitude is 15 kilonewtons. Let's go to the third member, is this one. We just calculated that it's under compression, and the magnitude is 21.21. So let's draw it. Minus, and the magnitude is 21.21 kilonewtons. And our last member is this one. It's under axial force 15 kilonewtons, compression, so it's minus again, minus 15 kilonewtons. Now we are done with the first member, with the axial force diagram. Now let's draw the shear force diagram, or the shear diagram. So let's show the arrows again. That's the shear force. Again, let's start from the first member. Now, it goes from bottom to top, so I have to rotate that in this direction. When I do that rotation, the shear force, the positive shear force, is in that direction. But if you look at this diagram, they are in the opposite direction. So at the bottom, I should have a negative 15 kilonewtons. Let's show it. 15 kilonewtons, and that's negative. Let's take a look at the top now. Again, I'm rotating this by 90 degrees. Then this will be the positive direction. Take a look at this 15 kilonewtons. They're in the opposite direction. So at the top, I also have minus 15 kilonewtons. What about the variation? I don't have any loading on this member. So it's again a constant variation. Let's jump to the second member now. We go from left to right, top in the upward direction on the left hand side is positive, so I have positive 5 kilonewtons here. So let's draw it. Plus 5 kilonewtons, and this is plus. On the other side, at the end of the member, I got 15 kilonewtons in the opposite direction with my positive shear direction. So at the other end, I should have minus 15. And this is minus. What about the variation? Now I'm looking at the load. I have a point load here. So up to the point load, I should have a constant shear and then a jump in the shear force and then another constant shear. So up to the middle of the structure, I should have plus 5. And at the middle, I have a variation, a jump whose magnitude is 20. And again, another constant shear. And this is negative. So we draw the shear diagram of the second member. Now the third member is this one, is the inclined member, and we find out that the shear force is equal to 0. So no shear force on this one. And then the fifth member, again the fifth member goes from bottom to top. Rotate that by 90 degrees. It goes from bottom to top. That's the positive direction. That's the positive direction. So at the top I have plus 15. At the bottom I got minus 15. So let's show it. Here I got plus 15 and here I got minus 15. What about the variation again? I got a point load. So it means that up to the point load I got plus 15 and then a jump whose magnitude is 30 kilonewtons and then a negative shear. And that finalizes our shear diagram. Now let's draw the moment diagram now. Okay. So let's start again from the first member, from this one. Rotate that by 90 degrees. So this will be the positive direction of the moments. Here I have a positive 26, right? Same direction. And at the top, it's in the opposite direction and magnitude is minus 4. So we start with this one. 26 kilonewtons and I got minus 4 here. Variation, shear force, I have a constant shear force. It means that I have a linear variation in the moment. So let's draw it. This is plus, minus, and 4 kilonewton is the magnitude of that moment. Now let's take a look at this member right now. At the beginning I have plus 6, at the end I got 0. So let's show it. This is 6 kilonewtons and 0 here. What about the variation? I should be looking at the shear diagram now. Now up to the middle the moment should increase, okay, and then afterward it should decrease. How much increase will I get? I have to calculate the area under this rectangle. 5 times this distance is 0.6. So the increase is 3 kilonewton meters. So up to the middle I see an increase. And this moment is 9 kilonewton meters. And then it should decrease and become equal to 0. And that will be the moment diagram for the second member. Third member, no moment, 0. Fourth member, at both ends I have 0 moment. And if you look at that diagram, we go from bottom to top. So the moment should decrease first and then increase. So I should have a moment as follows. This is minus, and the magnitude of that moment is the area under the rectangle. And if you calculate that, that moment will be equal to 9 kilonewton meters. If you have a problem with the directions, if you question why we have a negative moment here, you can just do this. Take a section cut from here, right? In order to balance this 15, I should have a moment in the opposite, in this direction, and rotate that sign convention. This will be the positive direction, but here I see a negative moment, and we have a negative moment here. So that finalizes our discussion on the internal force diagrams. Now we will be looking at calculating the deflections.